Welcome back. In this video, we will solve 2 sum 2 input array is sorted using the two-pointer pattern. We will go step by step, understand the idea clearly and see why this approach works. This problem is a classic example of how sorting allows us to solve problems more efficiently using two pointers. Let's start by understanding the problem. We are given a sorted array of integers and a target value. Our task is to find two numbers whose sum is equal to the target. Instead of returning the values, we must return their one-based indices. It is guaranteed that exactly one solution exists. Let's look at an example. Here is a simple example. The array is sorted and the target value is 9. If we look carefully, the numbers 2 and 7 add up to 9. Since we need to return indices, we return their one-based positions. Now that the problem is clear, let's think about how we might solve it. The most natural way to think about this problem is to check every possible pair. We take the first number and pair it with every other number in the array. So the pairs starting with 2 are 2 itself, 2 3, 2 7, 2 11 and 2 15. Now pairs starting with 3 are 3 itself, 3 7, 3 11, 3 15. Now pairs starting with 7 are 7 itself, 7 11 and 7 15. Now pairs starting with 11 are 11 itself and 11 15. And pairs starting with 15 is 15. In this way, we end up checking all possible pairs. This approach will eventually find the answer, but the number of comparisons grows very quickly as the size of the array increases. Because we are effectively using two nested loops, the time complexity of this approach is O(n) squared. The problem with this approach is that we are ignoring an important property of the input. The array is already sorted. When the array is sorted, not every comparison gives us new information. This means we can avoid many unnecessary checks if we use the sorted order intelligently. This brings us to the key idea of the solution. Here is the key insight. We place one pointer at the start of the array and one pointer at the end. We then look at the sum of the values at these two positions. If the sum is too large, we move the right pointer to the left to reduce the sum. If the sum is too small, we move the left pointer to the right to increase the sum. Because the array is sorted, every move brings us closer to the answer. Let's turn this idea into a clear set of steps. We start by placing two pointers, one at the beginning and one at the end of the array. While the left pointer is before the right pointer, we calculate the sum of the two values. If the sum equals the target, we return their one-based indices. If the sum is greater than the target, we move the right pointer left. Otherwise, we move the left pointer right. Now let's write this logic more formally. This logic can be written as pseudocode. The pseudocode follows the same steps we just discussed, without focusing on any specific programming language. Once this is clear, writing the actual code becomes straightforward. Now let's look at the LeetCode implementation for this problem. Let's restate the problem clearly before writing any code. We are given a sorted array of numbers in non-decreasing order and a target value. We need to find two different numbers whose sum is equal to the target. Instead of returning the values, we return their one best indices. It is guaranteed that exactly one valid answer exists. Let's look at a small example to understand this. 2, 7, 11, 15, target equal to 9. Here output is 1 and 2 because the sum of 2 and 7 is 9. So we return 1 and 2 because we have to return the one best indices. These are the other examples. Now let's look at the constraints. The array can be large, so checking every possible pair would be too slow. A solution that checks all pairs would take quadratic time, which is not efficient. But we are given an important hint. The array is already sorted. We should use this properly to design a faster solution. Because the array is sorted, we can use two pointers. One pointer starts at the beginning of the array and the other starts at the end. We look at the sum of the two values at these points. If the sum is too large, we move the right pointer left. If the sum is too small, we move the left pointer right. We keep doing this until the sum matches the target. Now let's translate this idea into code. We start by initializing two pointers, left and right. Left will start at 0 and right will start at n-1. Inside the loop, we calculate the sum of the values at these two pointers, and the loop will run till left is less than right. Let's find the sum. If the sum matches the target, we return the one best indices. If the sum is greater than the target, we move the right pointer left. If the sum is smaller than the target, we move the left pointer right. Because the problem guarantees one solution, this process will always find the answer. Let's run the solution. It's accepted. Let's submit it. Submission is also successful. Each pointer only moves in one direction and never moves backward. So, the total number of operations grows linearly with the size of the array. We also don't use any extra data structures. That's why this solution is both time efficient and space efficient. Now let's go back to the slide and walk through this step by step. Let's now dry run the algorithm step by step. We are given the sorted array 2, 3, 7, 11, 15 and the target value is 9. Initially, the left pointer I is at index 0, pointing to the value 2. The right pointer j is at index 4, pointing to the value 15. We calculate the sum of these two values. 2 plus 15 equals 17. 17 is greater than the target value 9. Since the sum is too large, we move the right pointer one step to the left. The left pointer stays where it is. Now let's look at the next state. The left pointer I is still at index 0, pointing to the value 2. The right pointer j has moved to the index 3, pointing to the value 11. We again calculate the sum. 2 plus 11 equals 13. 13 is still greater than the target value 9. So once again we move the right pointer one step to the left. The left pointer remains unchanged. Now let's evaluate the next state. The left pointer I is at index 0, pointing to the value 2. The right pointer j is now at index 2, pointing to the value 7. We calculate the sum again. 2 plus 7 equals 9. This time the sum is equal to the target value. So we stop the process here. We return the one best indices of these two elements. Index 0 becomes 1 and index 2 becomes 3. So the final answer is 1, 3. This is how the two pointers move step by step until the correct pair is found. Let's quickly look at the edge cases. The smallest valid input contains only 2 elements. In that case, the two pointers immediately form the only possible pair. The solution can also involve the first and last elements of the array. And since the problem guarantees that exactly one solution exists, we don't need to handle cases where no answer is found. So the algorithm safely works for all valid inputs, including the negative numbers, as long as the array is still sorted. Let's look at the time and space complexity of this solution. The time complexity of this approach is O of n. This is because each pointer moves at most n times. There are no nested loops involved. The space complexity is O of 1. We only use 2 pointers. No extra data structures are required. This makes the solution efficient for large sorted arrays. Let's quickly recap the two-pointer pattern. When the array is sorted, using 2 pointers is often a good choice. Here is the pointer strategy. We place the left pointer at the start of the array. We place the right pointer at the end of the array. If the sum is too big, we move the right pointer to the left. If the sum is too small, we move the left pointer to the right. This way, the pointers move toward each other until we find the required pair. We typically use this pattern when the array is sorted, when we need to find a pair or comparison, and when we are looking for an O of n solution. This approach works in one pass, uses no extra space, and is a common interview favorite. Now let's try one example on your own. You are given the sorted array 1, 2, 4, 6, 10. The target value is 8. Using the two-pointer pattern, find the one best indices of the two numbers that add up to the target. Pause the video here and try to solve it yourself. Start with one pointer at the beginning and one pointer at the end of the array and move them based on the sum. That brings us to the end of the 2SUM2 input array is sorted problem. If this explanation helped you to understand how the two-pointer pattern works on a sorted array, please give the video a like. If you are preparing for coding interviews and want to learn patterns step by step, consider subscribing to the channel. In the next video, we will continue with another two-pointer problem and build on this idea further. Thanks for watching, and I will see you in the next one.